Okay, so in the last video we saw how the state of a qubit evolves through a rotation of the space. So now let's try to understand this a little better. So, well, last time we talked about how, for simplicity, we thought of the qubit as having a real amplitude. So we could represent the qubit on the two-dimensional real space. And then we talked about how rotating the space, when you rotate the space through theta, you can write down a rotation matrix R sub theta, right? Which says how the state of the system evolves. So, for example, if the state was psi, then after the rotation it would become R sub theta times psi. Now, in actual fact, a qubit sits in a two-dimensional complex vector space. And so we've got to describe what the rotations of this complex vector space look like. Okay, so rotations of this complex vector space are called unitary transformations. Okay, and they are also specified by 2x2 matrices. So our complex rotation is going to be specified by a matrix like this, A, B, C, D, where A, B, C, and D are complex numbers. And what we are saying is, if we start with a state psi, then under this unitary transformation, it evolves to the state u times psi. Okay, so now let's try to understand what happens in different cases. What happens if psi equal to 0? What is u times psi? Well, remember psi equal to 0 means, well, 0 is also another way of writing it in standard vector notation would be as this vector, 1, 0. And so if you multiply u times this vector, you would get the vector AB, which is A0 plus B1. And similarly, if you start in the state 1, it gets mapped to C0 plus D1. Okay, now saying that U is a unitary transformation, or it's a rotation of the two-dimensional complex vector space, it's equivalent to saying this condition that U times U dagger equal to U dagger times U is the identity, where U dagger, it's the conjugate transpose of U, meaning first we take complex conjugates of all the entries and then we transpose. Or we do it in the opposite order, it doesn't matter. So, meaning this one would become A conjugate, complex conjugate, D complex conjugate. But these two entries are going to be exchanged. So this entry would become C conjugate and this would become B conjugate. Okay. So now, one of the conditions we want from this rigid body rotation is that angles are preserved. So for example, if we do the rigid body rotation on the standard basis 0 and 1, what we want is that angles and lengths are preserved. So we want that since we started with a unit vector, this should still be a unit vector, meaning that we want A squared plus B squared equal to 1 equal to C squared plus D squared. Right? We also want that these two should be orthogonal because A0 and 1 were orthogonal. So we want, for example, A star C plus B star D equal to 0. So the inner product between these two is 0. Okay, now you can see that these conditions are expressed here in this, because when you look at U dagger times U, well, this is A star, B star, C star, D star times AB, C, D, which is what? Well, this is supposed to be the identity. But as you can see, this entry is just the inner product of AB with itself. It's just magnitude of A squared plus magnitude of B squared. And similarly, this entry is magnitude of C squared plus magnitude of D squared. Whereas this entry is the inner product of AB and CD. And so this is saying that these two vectors are orthogonal. This says the same thing, and these two say that the length of the vectors are preserved. Another property of of unitary transformations, these rotations, is that they are linear. Right? This is what gave us the right to specify the rotation by a matrix. So what this means is that if you say that U times, if I tell you what the unitary transformation does on 0, let's say that it maps it to phi 0, which we were calling A0 plus B1. And suppose it maps 1 to phi 1, which we were calling C0 plus D1. Okay. Now, we could ask, what does it do? What does U do to the vector alpha 0 plus beta 1? And the answer is, by linearity, it must map it to alpha times phi 0 plus beta times phi 1. Okay, and you can of course further simplify it and write what it looks like in terms of 0 and 1. You would just say it's alpha times A0 plus B1 plus beta times C0 plus D1, which is alpha A plus beta C 0 plus alpha B plus beta D 1. Okay, so the main point here is that we can specify this unitary transformation by saying what it does on each of the basis vectors. Okay, not just in 2 dimensions, not just for qubit, but this also holds if you were specifying what it does for, if you had a k-level system, then you could specify what the unitary transformation does on the k basis vectors, and you'd have specified the unitary transformation completely. And of course, there's no mystery to this, because as we said, the columns of U are exactly where you map each of these k basis vectors.